starting from here can be a little bit challenging, but it's just more fun, actually.
Okay.
I've been using the VGA cable for a long time, but you never know what's really happening for the bottom level communication protocol. It's really fun to learn how that works. Okay, so that's a VGA cable I haven't seen before. And from the textbook, probably you don't even have a textbook, but we do have a textbook, and most of the tutorials are actually from the textbook. I believe there are electronic versions you can buy online. If you haven't, you can go ahead and do so. But I have some chapters here already printed in the PDF that I can refer to regarding the VGA chapter. And these are the pin outs. Oh. So that's the pin out of the VGA port. And in the constraint file, when you are working on it, don't forget to uncomment that VGA portion of the constraint file, otherwise you couldn't do it. So these are just the certain pins on the FPGA. Okay, and the names of these pins are called like VGA, lowercase VGA red, VGA green, VGA blue, H sync, that's the horizontal line sync signal. I'm going to show you what is that, and vertical sync signal as well. Okay, so these are the pins that you have to use, and also it's being clocked. So you need a clock signal which is 100 megahertz, but we divide a clock by using an IP. This is a very interesting example to learn. You can actually make a clock divider by pulling that little IP core from the Xilinx. They actually provide it. You only need to put the clock, which is this 100 megahertz in there, and then you just choose what is the output frequency is desired. Then it's directly just to make that clock frequency available to you. It's very convenient. Right. Let's start from the top. You can see VGA, the standard industry standard timing has all different types of standards, but the most common one is 640 by 480. This is the one we're going to use. That's the number of pixels to show that video or image on the monitor. But however, it's not actually 640 by 480 pixels on the screen. They have some like sync signal where it's called front porch, back porch. I'm going to show you the timing diagram really quick. These are some of the clocks are not being used to display anything to the monitor. You just need to know. So if you work on the Verilog, you will be able to tell what these are doing. They are actually doing nothing except for the H sync. I think they just provide a little room for you guys to, if you want to make a bigger image, you can still do that. But now we are just using 640 by 480. That's a number of pixels that we can use as the maximum ones we can use, but you don't have to use all of them every time. You can see there's one example here. It's one of the main goals of this tutorial. Okay, it's very interesting application. So this is the FPGA, and eventually I showed a little picture on the monitor. Okay, so you have nothing else except for the FPGA. So everything was programmed in FPGA. And you got an image, you can take a picture of it and convert it into the data file. So the data file has all the pixel data as 8-bit data in the file. And then you load it to the memory when you program it. So the ROM memory will contain that data file, which is the image file in binary form. And then if you look at the Verilog, okay, and this is the memory, the connection to the memory. Okay, so the data file will be in the memory, and then you have an address to take out all the pixels out and then send it to the monitor or send it to the pins. You don't have to care about what's going on for the monitor. You just need to send the data to these pins. Okay, so the data is from the memory file being programmed into or being synthesized into the FPGA chip. Okay, and then it's just sending pixel by pixel to the monitor to show this little picture over there. Okay, that's one of the main goals of this project. And also there are some other examples like task 1, just show a white color background, nothing on it, just white pixels. Every single pixel is the same value, right? Just show a static image there, and then try different colors and switch between all the different colors for the. It's just providing a solid background. Okay. It's all from the FPGA, right? And then I think that's it. It's so for the lecture here is pretty simple, but we do have a lab to let you guys practice with the with the VGA protocol further. But won't be the lab this week because you haven't practiced with it yet. It's going to be next week's, actually 2 weeks from now, because we have this is a 2-week lab. We're going to cover that pretty soon. You know, expect there's a VGA lab from now, 2 weeks from now. Okay, just more details in there. And let's get into the code and see what's happening. So this is the standard timing of the VGA, and specifically it is 640 by 480, which is the one we use. Okay, and you can click this link and look at the details. So all these details are, so these define the standard timing of the 640 by 480 protocol. And now look at what are the details over here. Okay, so the screen refresh rate is 60 hertz. Is that good enough to show, you know, videos? What do you think? I mean, it refresh images 60 times a second.
Yeah, it's normal.
It's pretty fast actually. You know, the ones I'm recording right now, okay? So this one, and when I convert into videos, it's only 30 frames per second. But when you watch the YouTube video, it's okay, right? It's not like really, you know, stacking somewhere, look like a static image. It's not. It's pretty smooth. So 60 will be pretty good actually. It's double the rate as the ones I'm using. And then from the calculation, because we know that there are 640 by 480 number of pixels. However, including the other, you know, so this is a image, the data range. You can imagine if this is horizontal, as a vertical, then it has 480 pixels in this range, or during this time frame. And if it's horizontal, then there are 640 here. They have to include all the other clock. So these are being clocked, okay? And every pixel got a clock. And then after that range, there are still some room. You have to do it. I think these are being reserved for a bigger image. And this is for sync. You know, whenever you are sending pixels all the time, but how the monitor know, like you have to change the line. They have different lines, and whenever it's done for the whole image, it has to send a signal to tell that the whole picture or the whole frame is done. So here you need a sync signal. So for the vertical sync and the horizontal sync. So whenever you finish the whole frame and you send a vertical sync signal, tell the monitor the whole picture is done. So I'm going to start a new picture. So all the pixels I'm sending after that, it's going to be the pixels for the next frame, not this current frame. So the image and videos are not being distorted. So same thing for the horizontal lines. Whenever you are done with the line, you have to change to the second line, switch the line. That's why you need to send a H sync, which is a 0. Okay, send a 0 here. And we just have to program it in Verilog to implement it. So now, for each row, you can tell, oh, let's look at here. For each row, this part is 640, and including this, and this, and this, that's the whole line. So for the entire line here, is actually not 640, it's more than that. So for the 640 by 480 standard, the horizontal number of pixels, or the number of pixels that taking the time to finish the scanning, is actually 800. You can look at this table, right? The whole line actually has 800 pixels. Okay, but only 640 is being used as a display on the monitor. All the other ones are just a timing for something else. Right? It didn't do anything. It didn't send any data to it. Okay, and you shouldn't send anything to it after 640. And for the vertical, right, it's 640, but actually 800 for the whole monitor. And then for the vertical dimension, it's not 480, right? 480 just for data, and it's actually 525 for the whole vertical line for each column. Okay, just need to know that you need to finish all these 525 in order and before you change to another frame for the vertical, and you have to finish all the 800 pixels assignment after you change the line to the second line. Okay, and these takes 10 pixels, 2 pixels, and 33 pixels. So I verified the calculation by giving you some examples here. So let's see if this makes sense. Okay, let's see it. Just do the calculation really quick. If it is 800 pixels each line, horizontally, 800 pixels, and each pixel is being assigned at a 25 point something megahertz. Let's just assume it's 25 megahertz, which means every pixel takes 1/25 megahertz, that much second to be done. So each line assigning a pixel for one line takes 800 times this. Does that make sense? That's how much time it takes to finish each line, right? And because you have 800 by 525 for the whole picture, so this is the number of pixels in total for each frame, and this is the time takes to assign one pixel. So this becomes what? Finish one frame. Okay, so in that case, after that much second, you have to change the next frame. So which means that becomes refresh rate. And then you can find out this is exactly 59.99 hertz, which is 60 hertz. Okay, that's how that works. So in your Verilog design, you need to create a 25 megahertz clock to do that, to send the pixels out at 25 megahertz in order to make a 60 hertz refresh rate. Make sense? Okay. And the from port, which is the timing here, okay, so you don't have to dig too deep into it. It's just a reserved timing on the timing diagram. So this one has 16 pixels of time. See, 16 pixels. Oh, that's horizontal. Horizontal is actually here, right? So this part is 16 pixels of time. And this is the time takes for each pixel, right? 1/25 megahertz. So which means the from port on the timing diagram takes 0.6355 microseconds. And if you look at the table, it's exactly the time we expected. And you can verify all these things by doing a very simple calculation to verify it. It all makes sense. Okay. So your role here is to program your Verilog and to program, to match whatever is showing in the table and to make it work. Okay. You are computer engineers, not embedded or C++ software developer right now. You are working at the very bottom level, down to the timing level. You have to care about the timing diagram instead of just getting the libraries from Arduino and program it. It's very high level, but now it's very bottom. And one layer down is going to be VLSI, but we don't have to care about the transistors right now. It's a block, all blocks, the gates, blocks, or register level actually. That's why it's called RTL. It's register transistor level language. When you program Verilog, did you program PMOS and NMOS in there? Like you program PMOS that has to be on the top and in parallel and NMOS in series at the bottom in order to make a NAND gate. You didn't do that. So it gets down to the gate level. Sometimes you do all the operators, the AND or XOR, they are down to gate level operation, not one layer down. So this is one layer up from VLSI, but one layer down from VLSI becomes engineering 430 you are taking with circuit guessing right now. That's one layer down. Okay, but this IPGA is one layer up, and Arduino is one layer up from IPGA. And but algorithms 1, 2, and C++ is one more layer up from Arduino, right? These are all the different layers from for the computer science area. Okay. Another thing you need to know, even though you have 640 pixels here, like horizontally, 640 pixels to display an image, but you don't have to use all of them. So for example, the picture I just showed you is a little tiny picture being shown on the monitor, right? The one I just showed you, right? This one. So it's only 80 by 80 or even smaller. So I just use the 80 by 80 sometimes. So you don't have to use all of them to save some time. And you can see the H-sync signal is a hardware, it's a one pin on the VGA's pin out. So the signal being sent to the monitor through that little pin on the VGA port. Okay, so it's just one line of signal. So you have sync here, and these are voltage lows or logic zeros, which is the signal being that you have to use to sync it, because the monitor has another control chip. So you are going to program the controller, VGA controller, onto the IPGA. So you are the engineer to engineer it, right, in IPGA. But however, the monitors, they have receivers inside as well. So other engineers who develop the monitors, they already put all the logic in there. So you don't have to worry about that, because we know the standard is 640 by 480. So we are going to match the technology together, since we are following the timing here. So if you look at the sync signal has to take how many pixels of time for the horizontal line? How many pixels of time it's going to take for the sync pulse, which is logic 0? How long it takes? It's not just the one falling edge. It's actually a period. It has it's a period of time, which is doing a lot of pixels, taking a lot of pixels time. So sending each pixel is 1/25 megahertz, right? So it has, for the horizontal sync pulse, it takes actually 96 pixel assigning time in there. Change the line. Oh, for the horizontal timing, it changes the line. For the vertical timing, it changes the frame. Because whenever you're done with the whole frame, it's assigning like this. Okay, yeah. That's why when it's done with all these vertical pixels, which means it's going to be out of range. So the next pixel has to be the next frame's pixel, right? Has to sync it. So I have to tell the monitor, then have to refresh it or change to another frame. So for the vertical timing, the sync pulse is only 2 pixel assigning time units. Okay. You don't have to care about why, it's just the standard. It's being being engineered into the chip, the receiver in the monitor. Okay, so we need to know that, so we can program in Verilog to design our VGA controller to serve that purpose. So now this is whatever you are going to program or design into the IPGA. Okay, you have 2 blocks. One is the ROM, stores all the data, the images data in there. So you need an address for it. And whenever it's not being clocked, keep in mind. Do I have a clock signal for the ROM? No. So whenever this address is a 13-bit address line is being sent to it, it has a decoder, but you are not designing the decoder, because you just write it in Verilog. Whenever you receive this address, you just take that data out. It's very simple. It definitely is going to synthesize decoder inside, but you don't have to know it. It's different from VLSI. You have to design every single thing by yourself. So this is going to directly do the job for you. And the ROM, I think we're going to use a IP from the Xilinx from Vivado as well. So it's just receiving the address data, and then it's going to directly send out the corresponding pixel data at that address. Okay, so 8-bit pixel data. So the 8-bit pixel data contains the RGB data in there at the same time. So that data has, if you look at the code, see? So this is the VGA control module, okay? For red, green, blue, okay, these are the VGA controller side. I mean, they will receive the data from the ROM, and it's how many bits for each color? 3 bits for each color. So you have 3 colors and 3 bits for each color. What's gonna happen? It's 9 bits, right? Yeah. So actually, one of the bits is not being used. So which means one color only has 2 bits. That's why 8-bit VGA data is not giving you a perfect picture. It's not really, you only have like 2 bits for one of the 3 RGB colors, right? It's only 4 options. Only 4 options to resolve all the different color ranges for that single color. So it's not making, if you look at the quality of the image, you know, our Basys 3 board is kind of blue, right? You can see the color being shown on the monitor. It's kind of turning green. So that's why it's giving you the 8-bit resolution. It's not giving you a good quality of the image. If you want to have a better quality of the image, you need how many bits? So how many bits can you have as a maximum here? You have to look into this constraint file. So if you open up the constraint file, you can see how many bits are in there available for RNG and Bs. So I think it is like 4. Could you open up? Probably not. Let's don't do it here. I think it's somewhere around 4, but we're not using all of them. We just want to make it fast. So 8-bit is very simple, and we don't have to use all of them. You can see that we have, even though we have 0 to 2 for each inside the VGA controller, but for the top module, for the test bench, we're not using all of them. We only made a connection. We only have 0 and 1 for the blue color. So we're only using the lower 2 bits of the blue color here. Does that make sense? I know the VGA controller has that 3 bits available, but because I'm just trying to use the 8-bit data for the top module, so I only assign 0 and 1. I just claim 0 and 1 for the blue color line, and then I just made a connection. So these outputs are the lines you created in the VGA module, or they are the physical lines on the FPGA? Yeah, why? These are like the LEDs, SW, and SEG, the SAG, and all the other signal lines you have used, right? These are keywords. You want to use it for some other purposes, right? If you have the constraint file has the same name here, then on the top module, they are going to make the connection to the FPGA. There are physical lines on the board. Okay, so you are not, even though you have all the other pins available, more bits, number of bits available on the FPGA board, but you are not using them, like the switches. You don't have to use all of them all the time, right? You can just use like lower 4, lower 3 bits. Same thing. I'm just using the lower 2 bits of the blue line. That's why you got a poor quality of the image. Make sense? Okay. So now let's see the internal structure. You are not wiring this up, right? So what you are doing just programming Verilog. So you need to think about that. What you want to put in the FPGA. In the FPGA control, a VGA controller. So the VGA controller receives data from the ROM. So the ROM is nothing but just stores all the image data. I have that data online. You can directly download it. and follow the steps to store it into the ROM IP from Vivado. Okay, it's going to be another module. It's another chip inside the FPGA chip, which is the ROM memory, stores all these image data in the binary form, right? And that's one module inside the FPGA. And then you have to program another VGA module. It's called the VGA controller. The very bottom level controller. The VGA controller communicates with the ROM, take the data from the ROM, and then send it to the monitor. That's it. And I wrap them up into one top module, which is a box I drew here, right? So this box is a layer communicates with the physical lines of the FPGA, the physical ports on the FPGA, according to the constraint file. And also it wraps the VGA controller and the ROM into that box. So in the Verilog file, you can see that, but also, yes, you need a clock, little clock module here to divide the 100 megahertz to 25 megahertz according to the timing standard of the VGA protocol. So that's why I used another clock module here. Okay. So let's talk about this first, then we jump to the clock. Okay. So see, address is available, data will get into the VGA controller, and the VGA controller will, so these are the number of rows and lines I want to use instead of 640 and 480 because the image is so small. So I just defined an 80 by 80 area to display that image, which will save some time and probably make it faster since I don't have to use all the pixels. Okay, so I just defined two local parameters or constants in there to limit the counts. And so the VGA controller, it's going to count according to the, the 25 megahertz timing. The timing the clock comes in whenever it reaches 800 by 525, right? Remember the whole number of pixels in every frame of the VGA protocol. And whenever all the pixel assignment is done, I need to send a VSync signal. Here's a VSync signal to the FPGA, the physical pin on the FPGA. And for each line, whenever it finishes each line, it's going to send the HSync signal, just pull it down to 0 and keep it low for 96 pixel time units. And to allow the monitor to walk through all the stuff inside. We don't know what's going on, but it just has to follow the protocol. It has to be 96. Has to be 96 clock cycles. Okay. And also, these are the data lines. 2 bits. No, 3, 3, 2. So 3 plus 3 plus 2 is 8 bit. So the every pixel is 8 bit. Okay. And here's the module and the VGA module, and this is the top. So as X, as Y, we defined these two parameters in the top module. You look at here, it's 80 by 80 because we know the image is tiny, so we just need 80 by 80 instead of 640 by 480, which is fine. And these are the parameters. H display is 640, is according to the protocol, and the V display is 480. Okay, and horizontal from perch 16 clock cycles, and horizontal pulse width, I think that's H-sync pulse width is 96 pixels or 96 clock cycles because the horizontal sync pulse is 96 clock cycles, right? Okay. And then, so if you look at the timing diagram, you just have to cover all of them, starting from here. And stop at here is going to be the H sync, right? So the H sync from here to here, that's 640, right? And from here to here, that's the front porch. Let me know how many. 16. And then from here to here is how many? 96. And from here to here is how many? 48. So in total, it's going to be 800. All right. Now let's see if I have all of them covered in the code. Right, 640, 16, 96, and 800 for the total number of pixels. And for vertical, as same, just refer to the table and put the numbers in here. And now it's just what you are going to do is just have all the counters. It's counting from 0 to 640. Then I know I'm done with the data. Then count for another 16. Then I know I should pull it down for 96 counts. And then for the rest, then I'm done for the whole line. Same for the vertical as well. So I have the counters, H counter and V counter. H counter counts all the pixels in a row. V counter counts the number of rows I have already. So enable 0. If I have enable 0, I don't want to do anything. I just do something when enable is 1. So I'm going to assign real pixels to the monitor, to the pin. So it's a very simple if statement. Let's go through it right now. H limit. So what is H limit here? I defined this much. H means horizontal, right? So what is H limit? It's just 800, okay? If H count is lower than this, it makes sense, 799, because from 0 to 799 is total 800, okay? So if this is lower than that, which means it's not going out of range, I don't have to sync, right? I don't have to do the H sync is already done. I have to count. Before it finishes 800, I have to keep counting, okay? So that's why H count plus 1 assigned to H count, no problem, okay? Else, what does else mean? It's out of range for the H limit. It counts towards, the count is probably 799 already. It's not lower than 799 anymore. It's equals 799. So I want to stop. So just clear H count. So you can start another line to start from 0 to another 799. Make sense? Okay. Right? Okay. So if H count is within range of the row, then I keep counting. If it's out of range, then I clear it. And if the V count is lower than the vertical limit, how many is it? What's the number in there? 525, remember? That 525. See? Okay. If it is within the range of the vertical of each frame, 525, then just add 1 to it. Okay. Otherwise, clear it. So these all the if statements over here, they run in parallel. See, this is an independent if statement, and you start another one. If V count is larger than SY, that's the image, that's the data. I defined it by 80 by 80, which is the data, the range of the data that I want to show an image in there, right? So it's 80 by 80 pixels that I want to send the data to the monitor, right? So if it is out of range of the data, then I assign -1 to the pixel address, because next time when it's within the range, I have to add a 1 to it. So we want to start from 0. That's why if it's out of range, you want to assign -1 to it. Because every time it is within the range, it's adding a 1 to it. That's why you want to start from -1, because adding a 1, it becomes 0, which is the starting point. Okay, so if it is out of range of the data, the 80 by 80, the pixels, then clear that address and don't enable anything, because you're not going to send anything out. Just disable it. Else, again, what else means here? Just for this if statement, right? Else means it's within the range. It's not larger than SY, which means it's within the data's range, the pixels range. Right? Okay. So when the y is within the range, then you have another embedded if statement, okay? When y is in the range, if x is also in the range, then I want to enable it, which makes sense. It's within that 80 by 80 range right now, okay? So I enable it, and also add a 1 to the pixel address. Just keep moving the pixel assignment on the monitor. If it's out of range, then just disable it, okay? So now it defines when you want to enable that pixel assignment over here, right? So now you know that whenever enable is 1, which means it matches whatever already designed over here, it's just in parallel circuits. Whenever that signal is enabled, I'm going to send the data to the red, green, and blue. Keep in mind, red, green, and blue are physically shorted to the red, green, and blue data lines on the physical board. Yeah, this can be confusing, but you have time to go through this by yourself later, okay? Yeah, that's why for the coding class, it's not making sense to keep talking for the whole class. It's just you have to go through it by yourself, program it. All right. So if it's enabled, send the data out. And if it's not enabled, send a 0 to it. That's why you are seeing black background, because it's not in the range, then it's all zeros. Okay, so it's black. And then if H count, this is something you need to know. I just want to explain this really quick. So I have another two if statements to do the sync signal, all right? So for all the programming on above, we didn't do anything about the sync, H sync and V sync, did we? There's nothing about the sync, right? Yeah. That's why I have to deal with it later. So if H count is larger than this but smaller than this, lower than this or larger than this, then you want to send a sync, keep the sync signal to be 0. Does that make sense? I mean, why it has to be within that range? So H display is 640. The front port is 16 for the H, the horizontal range. And this is everything. This is everything. Okay. See the H when it is larger than this plus this, but it's lower than this. So during this time frame, during this period, you want to assign 0 to it. That's 96 counts in there. It's not just the one clock. So whenever the counts falls into that, you want to enable that sync. So 0 is enabled because 0 active. It's a low logic 0 in there. Otherwise, keep the H sync 1. Okay, it's the same for the V sync as well. All right, and that's everything about VGA controller. It's pretty simple. Okay, and you can see the pass edge is not the clock anymore. We're not using a 100 megahertz clock. Keep in mind, it's a modified clock. It's a divided clock from the IP. So this is how we declare it in the top module. So we have the clock module, we have the memory module, we have the VGA module. So 3 modules. We have the clock module, the memory module, the VGA module, right? That's everything we have in the top. And you can see the memory module, yeah, it has the address line and the serial data, the output. So these are from the IP. So you're probably wondering, where can I find the SPO? Right? Where's SPO? So when you design it from the Vivado IDE, so you can see the chip, the IP has the SPO, which is the output, and has the A, which is the address. Okay. For the clock, it's a bit confusing. So this code is directly from the textbook, right? So I directly use whatever they use. But do we understand what's going on? So this one doesn't have a dot, something, parentheses, something, make the connections, right? Could you do that? As long as you follow the order, you know what I mean? You understand that? So it has to follow the certain order. So for example,
like a function in C++, where it's like you put whatever in that, but as long as you follow it.
yeah. So for example, this one, if I don't put the parentheses pixel address or pixel data in here, I just remove it, still fine, as long as it follows the order. So I have the order of output. This is 25 megahertz, which is the output from this module, right? And this is the input. Okay, and now let's look into this module, inside the module, what's going on there. If we find the module here, right? So after I just use it from the Vivado IDE, right? It's actually create a file, but you can open it up. So that's how I open it. It's also a Verilog module, even though it's an IP, right? And now I can see that it defines output first and then input. Okay? Yeah. So if you follow the same order in your top module, and you don't have to, I don't have to put it in there. It just not saving anything but confuse people. I still prefer you put it in there, like put the parentheses and make connections. If you follow the order, it's fine. It will automatically make the connection by itself. Okay, and this clock is from the IP. You can see this clock. It's the IP, little IP module from Vivado, and it has a little Verilog file in there. So if you want to see what's going on inside, you can open it up and take a look at it. Okay, but this is a clock module, right? It's the chip. Clock in, clock out. Right. Okay, so these are all the connections we already went through, and no problem here. The top, no problem. Just want you to understand what's going on here. So again, what are these ports? Are these ports from the module or from the top? They're from the top. So these are the signal should be put into the parentheses actually.
You do it from the Verilog file, you could do the dot, whatever they called it, clock out 1 or something.
Yeah, I just didn't do it. I just didn't write it down, right? Yeah. So, but these signals, you should know that these are, if you use a traditional way, they should be put into the parentheses, and you have a dot something parentheses clock 25 and dot something parentheses clock, right? Why did I know that? Because you can see I have clock and I have clock 25. Okay, so these are the signals from the top. And if you look at the clock IP, the name of the two ports are actually clock underscore in1 and clock underscore out1. Right? So these, if you do it in a traditional way that we have been doing, or this way, this format, it should be what? Dot clock out. Dot clock out1, parentheses clock 25, comma, dot clock in1, parentheses clock. Make sense? Okay. So if I change the order here, if I claim input first, output second, can you still do this? You have to, yeah, you have to flip, right? Okay. All right, that one is easy. And I should give you a VGA cable. I still have a lot in my office. Don't forget to get one from me after this. And modify the code. This is simple, right? Pretty simple tasks. Just show a solid image onto it. And constraint file, right? That's quite a lab. So Thursday is a FPGA day, right? FPGA lab, 2-week lab. Okay, notes is available, great. And video is here. Watch the video for the introductions. So remember in VLSI, oh, you haven't taken that yet. But you have taken logic, right? Yeah. Okay. For this is what? What is this happening here? What is this? Remember? Huh? Say it again. Yeah, what kind of adder? Yes, it's a 3-bit adder. And this is using 2's complement. So we are able to do both addition and subtraction. Why? But adding is just adding, right? Why you can do subtraction as well? XOR on the top. So if you XOR a data with 1, what's going to happen? So this is the 1, there's a constant. And that's the data, right? If A XOR with 1, what's the result? If A is 1, what is this? Yes. Okay. If A is 1, you're getting 0, right? If A is 0, you're getting 1. What's happening here? If something XOR with a 1, what's happening?
And it's changing its complement. Yeah.
It's inverting it, right? So what if I change this to 0? If A XOR with 0. If A is 0, 0 XOR 0 is 0. Yeah, they're the same number. XOR with each other is still 0. If A is 1, 1 XOR 0 is 1. Okay, so it's not changing A. So if A XOR with 0, it's not changing anything. Make sense? If you want to invert it, you just XOR that data with a 1. If you want to just directly send the data through that XOR gate, you just XOR that data with a 0. Okay, so I have a little switch here. If I switch this to 1, what's the output here? A naught for all of the 3 bits, right? If I switch this to 0, what's in here? Just A. So these are the inputs to the adder. If I switch this to 0, it's just A0 plus B0, and A1 plus B1, and A2 plus B2. Make sense? So it's an adder. If I switch this to 1, what's happening? I'm flipping A's, right? And then what's going to happen? Because 1 is just 1, it's also being fed into the C in. So what's actually happening? I'm flipping and add a 1. So that's exactly a 2's complement. 2's complement, so which means all the A's are being converted into a minus A. So B minus A is the same as B plus minus A. So it's still adder. You couldn't change the functionality of the adder. It's always adding, but we can flip A by 2's complement. Make sense? Okay. So in that case, if you are doing a subtraction, you just switch this to 1. So you can make it work, right? It's flipping each bit and also adding a 1 to it. Okay. And there are some other things you need to consider. Overflow, right? How to deal with overflowing here. And the overflow bit is actually you have to XOR C1 and C2. And why is that? I did a demonstration in the video. Okay. So that's just some technique to find out the overflow bit. And eventually just program this thing accordingly in Verilog. I think you did a 2-bit full adder, I think in one of the assignments. Yeah, it's very similar. You have to use a wire technology plus floating wire to make the connections. And these are pretty simple because it's just the extra logic and output being sent to A instead of directly using A. See what are the tasks. Use switches as a 3-bit inputs and use LEDs to show the binary results. And use switches as 3-bit inputs, use a 7-segment display. Okay, so the data should be displayed on LEDs as a 2's complement results, but also being showed onto the 7-segment display units. You just need a lookup table. Whenever you have this data as an 3-bit, 4-bit actually, if you have this 4-bit binary result, like switch case, right? In this case, you throw these data lines to the 7-segment display to show this number. You're telling the FPGA to show what in there. You know what I mean? Okay, so you need a lookup table. And I think
Right, so this is a quick introduction.
Or something like that. So I have zeros, this is 0. Okay. And you can modify the time delay. Let's see. So you can show a minus number there as well. Okay. If you have to show a minus number or negative number, you can see this is not perfectly clean because the time delay I had in the Verilog code. You can modify that time delay when you scan through in between the 2 units. You can modify that a little bit. I forgot increasing or decreasing it in order to remove that kind of ghost digit onto that unit, right? It's working. It's not too bad. Any questions so far? It takes time. This one is 2 weeks. I give you guys 2 weeks to work on it. I think you can take the time to build the lookup table. Just divide the entire project into smaller pieces. Sometimes you're tired, you want to work on logic, then just build the lookup table. It's very simple. Whenever you have this 4-bit number, you want to show what, right? It's physically on a 7-second display. You know which LEDs you want to light up. If you think you're smart that day, not tired, have a lot of time, you can work on the internal wiring of the coding. Right? Okay, so I'll be in my office. We don't have a lecture for the lab anymore. You guys just working on the lab, and I'll be in my office to help you guys out. Okay. All right.